Right, hello everyone. Right, we are continuing with our revision exercise. We want to locate loci today. Right, we are going to focus on the helix and the chem. These are revision tasks or revision exercises. So let's make sure that we iron out our understanding with regards to each topic that we touch on from now and onwards. Like I said, it's a revision task. We are looking at loci, that's the locus of a point as it moves. We are also looking at the concept of the helix as well as the chem. Right, specifically we are looking at question number 2 of paper 2. Right, this is from the past exam paper, Feb March 2017. Like I said, it should be within 5 years. Always look at approaches and applications so that you'll be able to apply the same concept on your own. Right, as always, I hear and I forget, I see and I remember, I do and I understand. The focus is to make sure that you are able to do the tasks on your own, and that is through application. Just a moment, let me close the window. Right, okay. The birds were singing. Right, so like I said, the focus is to make sure that you are able to apply the concepts that we talk about as we are looking at this revision time. So let's get straight to it. I wish you all the best with this lesson and hope you would enjoy it. Thank you. Let me just push this one slightly to the left. Right, okay. That's question number 2. Note, answer question 2.1 and 2.2. So the two sections of question number 2 would be put together and you would have a cumulative question number 2. Right, given the front part with regards to the loci, the helix, right, a front view and left view of the shaft of an auger with Q indicating the starting position, the position of point P on the drawing paper, specifications, nominal diameter. When you hear the word nominal, like we discussed earlier on when we touched the concept of helix, we say nominal is the same as maximum. That's the maximum diameter, okay? Here we've got 1.5 tenths. Then we've got direction, it's left-handed, but we shall take note of all this information later on. Then we are also given the shaft which is 108 and diameter 34, but that is the diameter which is also this diameter, right? Now instructions, draw to scale 1:1, the complete front view and left view of the auger, right? With regards to the left view, we are simply going to make use of point P, which is given. First of all, let's just draw a faint horizontal line like that. Then another one, it's a vertical line like this. Right. The next thing is to measure the shaft diameter, which can also be referred to as the minimum diameter. We know that the diameter is 34, right? That is from here to there is 34, so radius would be 17. So I'm going to measure 17. Right, and we are also told that the maximum diameter, which is the nominal diameter, is diameter 74, which means the radius is 37. Then we stand at point P. Right, and you describe a circle like this. This you can outline at once like that. Then you also do the same for the minor diameter. Like that. Then we can project from here. We can measure our 108. So we can just pick a position and like this. We measure from here to there. That's 108. Right. Like we said that the pitch is equal to 72. Right. So what it means is that half the pitch or half the turn, okay, remember the pitch, right, is equal to the longitudinal, which is a length, okay, from one point to the other, which is 72, and the turns, it's 1.5. Each turn would be equal to the pitch, which is 72. So half a turn would be 72 divided by 2, which is 36. So if we say 36 plus 72, we should get 108, which is the distance from here to there, which is the distance which is also given here, right, as our height of the shaft. Now, once we have defined this, right, what we can do, right, at this point, we can easily show the center lines. Like that. That's the vertical center line. Then we also need a horizontal line. Like that. Right. All those are marks, okay? All right. Then once we have done that, we can now divide the height of the shafts according to the distance or the pitch, which is 1.5. Right, we divide this one into, right, into 1.5, which is, remember, every turn is equal to 12 division. So half a turn would be 6 divisions. So altogether, you would find that we have got 18 divisions. So let's divide this one into 18. I'm going to use 5mm intervals. Like this, you connect the last point to the just making them cross slightly so that I'll be able to pinpoint the exact point of intersection. Like this. Right, there you go. Right, we are also told that our point Q would be here, right, which is also point Q and point Q, which is also in line with that point. Right, we divide the circle into the number of divisions in terms of one complete turn from here to there. But remember, our complete turn is equal to 12 divisions, so we do divide also this one into 12. Right, so this is our point 0, that's 1. Right, since it is left-handed, okay, right, if we turn this one around, you find that this would obviously should be at the top and is starting at the top there. All right, okay. Now, what it would mean is that, as you can see, this is starting at the top, but if it was here, right, if you would check this one, right, point Q is starting at the top. But since this could also be turned around and up like this would be the top view, this would be the what? The front view. Now, so if it is starting at the top, you maintain the direction, okay? Left-handed, it's anti-clockwise. Right-handed, it's clockwise, right? So in terms of numbering, right, like I'm saying, if this point Q was here, right, and they say it's left-handed, you are going to number 1, 2, 3. You reverse the direction, okay? But if it is starting at the top like that, you maintain the direction of rotation. So it will be 0.1, 0.2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Back to 0, okay? Right, for now, we are simply going to project from the outer one, right, like this, faintly. Skip that. We also come here. Do the same. Right. So we are saying this is point 0, where we can also write this is our 0. So we've got 1, 2, 3, 4, 5, and 6. 7, 8, 9, 10, 11, then 0, which is our pitch, our complete turn. Right, so then we've got 1, 2, 3, 4, 5, and 6, which is our half turn. Okay, but you need to understand all this in order for you to be able to answer this particular question. Right, now this 0 from here, so we've got a point common 0 there. Then we move to point number 1, which is this one, 1 and 1. Then we've got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which is our one complete 10. Then 1, 2, 3, 4, 5, and 6, which is half a 10. So we are going to connect this. Like that. So we have got up to this point, that's one complete 10, that's half a 10, okay? Right, once we have done this, then you look at this. We can now outline, right, that part of the helix which is going to the left. Remember, we are looking at left-handed, so when you are looking from this side like that, right, you would need to consider part of the helix which is moving away from you but also going to the left. Then that has to be outlined. So I'm going to outline this. Like that. Right. Then the from here all the way to there, it's now going to the right, but from here we also have got right. We also have got the helix, which is also going to the left. Then from here to there, it's now going to the right. So that's our first part. The next part that we want to look at is now with regards to the helix around the shaft itself. So we are going to project like this. Like that. This is the part which is secured on the shaft, like that. Right, point 0 would remain, which would be there. Right, so this would be 1, which is 1. And we've got 2. We have got 3, 4, 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4, 5, 6. Okay. Right. We connect this one faintly again. Like that. Now, once we have done that, right, we can also again outline that part of the helix, which is also moving to the left. Like that. Then we do the same, it's from here up to there. So we are done with the helix, right, which are going to the left. Right. The next thing that we want to do now, right, we can now define the shaft. But with regards to the shaft, the moment the helix is going to the right, especially with regards to the small helix, we then outline like that, straighten it. Then we also do the same outside the helix. There you go. Right. Then also outside the helix, we do this. We also come here and do the same thing. Remember, the shaft does not disappear. It's only that at some point it will be covered by the helix. Right. Then we also complete from this end. Then we close. We also close it to the bottom. Like this. Once we have defined our head, our shaft, we can then go back to that part of the helix, whether it is going to the right. We can now define it, then it will be stopped by the shaft. So we take it all the way, stop there. Right, they say no hidden details are required, so we are not going to define any hidden details, but it would also show here, right? We show it like that. And then we can also go this way. Right. Now we would have completed our helix in terms of the auger. Remember this, like we said when we introduced the topic, right? It's something more like a drill bit, okay? Drilling bit. If you want to cut through something, creating a hollow part, right? You would use something in the form of an auger, okay? But I'm just going to add a bit of graphics, right? So that you would appreciate what we have done. But remember, this is not important, especially if you are not done with your work. But of course, if you are done and you want to just show the examiner that you understand what you are doing, right, by any means, you can show this. Right, but also make sure that you are not going to erase or close off the construction lines. But they need to be seen. What is marked 80% of your work are construction lines. Then you also do the same this side. There you go. Right, so that is our typical example of an auger. Right, like do not waste your time trying to do this. There are no marks which are given for that, but we are learning. We just want to give, right, sort of a clear view as to how it would appear. So that's an auger. Right, okay. Right, if we are satisfied with this, we can move on to the second part. Right, the second part is about a cam. Right, let me push this one slightly. Right, it says, given the bottom left point or 0 degrees starting position of the displacement graph, right, if we check here, right, in terms of the information that we are given. You'd find that at the bottom there is 0.0, which is the starting position of our displacement graph. Right, motion. The follower rises with uniform motion for 15 millimeters over the first 30 degrees of rotation. Right, so it rises, right, for 15 millimeters, right, over the first 30 degrees in terms of the rotation. There is a dwell period for the next 15 degrees. The follower rises with simple harmonic motion for 65 millimeters over the next 135 degrees to the maximum displacement of 80 millimeters. So we are also given the maximum displacement, but even if you are not given that, you would look at the total rise in terms of the height. So the first rise would be 15 plus the second rise would be 65. If you add the two, you find that you end up getting 80. But we are also told in clear terms that is the maximum displacement. Right, there is a dwell period for 90 degrees. The follower returns with uniform acceleration and retardation to the original position of over the rest of the rotation. So the idea is for us now to look at these three key types of motion which are associated with the curve. That is the uniform velocity or uniform motion, also the simple harmonic motion, and the uniform acceleration and retardation. Right, so we want to look at the application of all these motions so that we will be able to do the same on our own. Right, instructions: draw to a displacement scale of 1:1 and a horizontal scale of 360, right, is equal to 180 millimeters. The complete displacement graph for the required motion, label the graph and indicate the horizontal scale. Show all constructions. So we make sure you are able to answer everything. But sometimes some people would leave out this aspect of the labels, okay? Right, it's not much, but it would add value to your marks. Right, we are told that that is just 1 mark. Right, like I'm saying, it's not much when you look at it, but 1 plus 1 would give you 2. If you continue to add something there, you'll get all your marks, okay? Right. So we are going to start our drawing now. Just take this one slightly up, like that, okay? But I'm going to, first of all, draw a faint horizontal line like this, right? Then a faint vertical line like that. Right, from 0.0 upwards, I need to measure the maximum of 80, which is the maximum displacement. So if it is a follower, it would move from 0.0 to the highest point, which is 360, right, with a displacement height of 80, like that. Then the next thing, right, we also need to measure 360 degrees, which should be represented by 180. That's 150. That's 180. Right, the first thing that you would need to do, once we have done this, right, you divide the horizontal displacement by 12 or into 12 equal parts. Right, to create intervals of 30 degrees, 30 degrees, 30 degrees. I'm going to do this, use the actual 12 millimeter, which is this one. Right, okay, and then we take our set squares, two set squares, align to the last one. Normally, there's a mark for showing these divisions. Right, so what we have is 0, 30, 60, and so forth up to 360 degrees. Right, so if we go back to our motion, it says the follower rises with uniform motion for 15 millimeters over the first 30 degrees. Right, so we go there, right? We can even take this and write that's 30 degrees. Right, we measure from here to there 15 millimeters. Right, on the 30 degree mark, we measure. When you mark. Remember, uniform motion is just a straight line. Then you connect like this. You get to this point. Then it says there is a dwell for 15 degrees, right? So we know that from here to there, that's 30 degrees, right? So if you want to get 15 degrees, you do this. Maybe let me just do it at the top so that it's clear, like that. Take your 45 degrees set square, like that. Then you take this one down, like that. Then straighten like that. Remember, a dwell, it signifies that the follower is not falling, it's not rising either. It is maintaining the same height. So from here, which is 30 to about 45 degrees, but the follower is maintaining the same height. So we are going to say 45 degrees. 30 plus 15, you would get 45. Right. If you want to be certain, we can as well outline this part. Like that. And do the same. Right. So we have defined the first part with regards to our displacement graph. Right. The next one, it says the follower rises with simple harmonic motion for 65 millimeters over the next 135 degrees to the maximum displacement. Right. So from here to there, right, it should give us 65 because from the bottom, from this point to that point, that's 80. Right. So we should be able to get 65, which is exactly that. Right. Now, if we say 135, right, 135 plus the 45 already used, we are going to get 180. So here is 60, 90, 120, 150, and 180 there. Right, so we are going to write here 180 degrees. Right, you identify and take note of those key positions in terms of the movement of the follower. Right, so from 45, it would go to 100 and what? 180 degrees. Now let's look at the divisions that we have. It's 1, 2, 3, 4, but we have got this one. It's an odd division, okay? Right, so what we want to do is to make sure that we have got a same number of divisions here as we are going to have for the semicircle. Remember, for simple harmonic motion, it has to be defined by a semicircle. So from here to there, right, from here to this point, it should be the same number of divisions from here to there. So just do this. Right, okay. Right, okay. So I'm going to divide from this point to that point 6 divisions, right, which we are going to disregard these ones, okay? So I'm going to do this, create a line here, like that, mark off 6 points, right, that's 1, 2, 6. Then we connect to this one. Take our set square. There you go. So we have got, at this point, that's 45. Right, so what we are going to check is how many degrees is each division from here to there. Right, if we are going to say 135 divided by 6, right, we'll find that each division from here to there is representing 22 and a half, 22 and a half, 22 and a half. Right, so I'm going to bring these divisions down. Let me use a different color so that we are able to see there's already something here, but faintly. But these divisions, they are 22 and a half, 22 and a half, 22 and a half. But once we have done that, we also have got to need to define from here to there half the distance. So what we can do is simply to do this. And we can miter like that. And also come here and do the same thing so that we get the midpoint. Just going to take it up to there. Then we take our canvas, using this point as our sender, open to there, right, and also open to there. Okay, that's fine. Describe an arc, a semicircle, right, like this. Right, I can stand here to divide this one into 6 equal parts. Stand there as well. Right, you do the same this side. So let me just Right, so if this is 45 degrees, right, 45 plus 22 and a half plus 45, but we'll find that the next point is 67 and a half degrees, which is this point, then plus 22.5, right, this one is 90 degrees, right, plus 22.5, but we are going to get 112.5 degrees plus 22.5. We have got 135 degrees plus 22.5. We have got 157.5 plus 22.5. We now have got 180. So this is 180 degrees. Right, so what it means is that this level and that level from here, we have got 180. So what is certain is that there should be a point here and another point there, 180 and 180. Then we can start by projecting from here. Right, remember that will be our face. So from here, like that. We have got, this is 67.5. Then we project from here. This is 90 degrees, right? We project, we have got 112. And we have got this one, which is 135. And last but not least, which is 157.5. But once we have gotten these points, you connect these points. Like that. If you are satisfied with what you did, then you can outline this. Right. If you want to take a breather, take it at a point. Right. There you go. Right. So that is the part with regards to the simple harmonic motion. But the next thing that we want to look at in terms of the motion, right? Sometimes it's necessary, just in terms of your drawing, right? I've answered this part you tick. I've also responded to that so that you don't leave out certain parts of the question. We did this one, right? So we can tick. But the next one, there is a dwell for 90 degrees. Remember the divisions from here to there, to there, to there, it's 90, right? 90 plus 180, right? We'll find that we get 270. Right, so here we are going to write 210, 240, and 270. That is the movement from in terms of the dwell. So it is maintaining that part at the top. So we are going to write here. Right, then the next thing that we are looking at, right, we want now to make use of the uniform acceleration and retardation, right? It should fall from there to there, right? Now we have got 3 divisions, right? Normally you'd find that in order to do the uniform acceleration and retardation, right, in terms of the smoothness of the curve, yes, you can still do this one with just 3, but it will be ideal if you create additional divisions as well, so that you have got 6 divisions. Right. So we are going to subdivide the 30 degrees like this, 45, 45. Like that. Then we take these ones down. But normally when you do this, you use a different color so that it's noted that this is additional, or you use a different line altogether. But just to note that this is additional, it's not part of the original division that you did. So now we have got 1, 2, 3, 4, 5, and 6 divisions. Once we have gotten those divisions, right, we can also create a number of divisions this side, but same number of divisions. But if there are 6 divisions there, we also create 6 divisions here. So we've got 1, 2, right? You take another set square. There you go. Right, so you've got 1, 2, 3, 4, 5, and 6. On the third one, which is 1, 2, 3, which is here, you also take this one to 1, 2, 3, which is the third point like that. Right, and also here, we do this, take them like that. Now, if we were to label here, right, we would say, right, because this is 270, right, so at this point, that's 270, and then 270, then this one will be 285, 300, 315, then 330, then 345, then you have got 360. Right, so 270 and 270, they would meet here. 360, which is here, and this also 360. Right. Now you find that later on, right, I don't want to do it now, but you should be able to draw a line like that. But remember, whenever you are doing uniform acceleration and retardation, from the starting position to the end position, there should be a straight line like that. Why? Halfway, we refer to this one as the first half, this one is the second half. Right, if you connect from here to there, right, it will cut this line, okay? Remember we said this is 285, this is also 285, but you don't need to write that. So there is the point that we want, 285 and 285, they are meeting there. You do the same. This is the first half, this is 300, right? Then from there, you go to 315, which is here, which is common. But the moment you reach that part, you now connect from the other end. We refer to this one as our second half, like that. You have got this point, then you do the same. Like that, you have got that point. Right. You connect these points. Like that, okay? But you connect those points, then you create a curve. All right, from a rapid fall, right? But remember, you need to gain some bit of momentum before you even begin to accelerate, right? So you go right slowly, then you gain speed in terms of your falling, right? But as you reach towards the end, you reduce your speed. That is retardation, okay? Right. So initially, you need to accelerate in terms of your movement, then you retard, you slow down as you reach the end. But once you have done that, we can outline this. Like that. Right. So that is our displacement graph, right, with regards to the application of the three motions that we looked at. Uniform velocity, which can also be regarded as uniform motion, right? Then the other one is simple harmonic motion, but which needs to apply or make use of a what? Of a semicircle, then the uniform acceleration and retardation, like that. Now, once you have done that, the last thing that you would need to do, right, is to label. Right, at the top there, you can label. Right, so this is known as the displacement graph. Like that. Right, on the left-hand side, right, you also have got, you can write this, right, displacement in millimeters. Right, the moment you say displacement in millimeters, you are also technically saying it's 1:1. Right, then you also indicate at the bottom right, it's a rotation in degrees. So you write that. In degrees. All right, you also indicate the scale is equal to 360 degrees is equal to 180 millimeters, like that. Right. When you have done this in terms of both questions, let me just take this one such that both questions would be visible. So this is how you would get all the marks in terms of question 2.1 and question 2.2. Right, out of 39, the first one's 23 and the second one 16 marks. Right, I hope I've tried to clarify all the issues that you had with regards to the displacement graph, given the types of motions, given the terms that are associated with the displacement graph. Right, and especially the treatment of these subdivisions, it's critical. Whatever number of divisions here, you may, right, decide to come up with your own divisions as long as you are able to plot that graph. Thank you and good night.